All right, today is our second day dealing with sine and cosine graphs, and our objective is to calculate and analyze features. This is pretty broad, but the thing that we're going to hone in on today is period because we have not yet covered it. So first thing I want to do is just remind ourselves that, hey, this stems from the unit circle, right? As we rotate around our unit circle, our height goes up, it goes down to 0, it goes negative. And as we trace that over the rotation or over time, we get this yellow sine wave. Same thing happens with our co-height or cosine. We are going to define the word period. We handled midline and amplitude the other day. Period is going to be the time it takes to complete one cycle. The units are going to vary depending on the context of the problem, which we'll see tomorrow. But we should assume that we're dealing with radians unless it's otherwise specified. So if we want to kind of illustrate what it looks like to complete one cycle, one thing we can do is we can go peak to peak. So if I take this peak here and I measure to the next peak, that distance there, that time, that will give me a period of my waveform. Another way we could do this is we could measure from the midline, trace one full rotation of a circle. So it's not here, that's half a rotation, it would be to here. This distance here would also give us one period. Our graph went up, it went down, it went back to center. So those are two quick different ways to measure our period. Tying this into our equations, let me go back here to our transformations. We should first kind of label this B coefficient that we ignored last lesson. Notice how we had amplitude and midline defined in terms of our equation. This B coefficient, the thing that is multiplying with x inside of our sine and cosine function, that is going to change the period. Notice how it's not the period itself. It's going to change the period. The way we can relate B to the period is through this formula here. So make sure to get this down into our notes that to find the period from our equations, we want to use this formula. Period equals 2 pi over B. And it stems from the idea that, hey, if we have a full rotation of our circle, one full rotation, that is 360 degrees, or that is 2 pi radians. And so that B coefficient is going to kind of screw with the frequency that we rotate around our circle. And so it's all kind of related back to that 2 pi radians for one full rotation of a circle. So with example 1, if we're trying to find the period, we should first locate what B is. And B in this equation is 4. Based on location, B is equal to 4. So if I want to calculate that period, I'm going to abbreviate it to PER, we just take 2 pi and we divide it by 4. So I can either write this in simplest fraction form, which would just simplify down to pi over 2. And this is in radians, so pi over 2 rad. Or if we wanted to calculate it out to a decimal, which we should get in the habit of doing both, we type in pi over 2. We get 1.57, so 1.57 rad is another way to express our answer. Both of those would be correct, pi over 2 or 1.57 radians. I'd recommend pausing the screen, trying this for yourself for the next two, but if you're just going to kind of follow along, feel free. So example 2, it's all about finding that B coefficient. So that B coefficient in example 2 is 6, so B equals 6. So that means that period there is equal to 2 pi over 6. That could simplify by dividing 2 from top and bottom. So we would get pi over 3 radians. Or if we wanted to simplify it into a decimal answer, we can change this in Desmos here. Pi over 2 would be pi over 3, so 1.05 radians. And again, that's how frequently we repeat. We're going to see this on our graph here, or our graph example is a lot cleaner, but just want to still get practice from working from the equation as well. And the last one, cosine 2x plus 5, the B coefficient is 2, so we get B equals 2. that means our period is 2 pi over 2. The 2's cancel each other out. We just get pi radians, which is half of a circle. So we're going to kind of repeat twice as quickly as we normally do. And if we calculate pi radians, we should know this off the top of our head, but we can also just plug it in. Pi is just equal to 3.14 radians. So I'm just going to write that in there. That is how long it takes us to repeat. So we can also determine this stuff from the graphs. In example 4, notice there's no equation here, just a graph. We are trying to find the period. There's a couple ways to go about doing this. We can measure that peak-to-peak distance if we wanted to. So you'll notice that, hey, we have peaks right here. There's our peak-to-peak. One of them is down at 5 pi over 2. The other is at pi over 2. So if you wanted to, you could go 5 pi over 2 minus pi over 2 to measure that distance. Let me throw a nice label in there if we wanted to. That would give us 4 pi over 2, which could simplify down to 2 pi radians. However, we can probably more quickly find this by tracing one full rotation. I'm going to do this one in green. If I find my starting point, so at 0 degrees, at 0 radians, it looks like I'm at 2. This conveniently is where my midline is at, but if I trace my graph, the graph goes up, goes down, it goes back to the start. And even though I'm back to the start, I haven't completed one full rotation, right? I also got to dip into that below midline area. So I dip down below, and then I come back to the start again. I'll notice that this point here lines perfectly up with this 2 pi radians. So we get one full rotation is 2 pi radians here as well. So two ways to do that, either measure peak to peak and subtract, or I really like tracing from the start and tracing one full rotation as a good way to calculate what the period is. We can see this in example 5 as well. So example 5, I'm going to start with the tracing method because this will be a little bit easier, I think. It looks like we're starting down here at 1. So I need to kind of trace and follow. My graph goes up, passes the midline, goes down back to midline, and it does complete one full rotation this time as soon as it hits back the center, or to where we started. Notice I've went up through the midline, down through the midline, and it looks like that finishes out at pi radians. So my period is just going to be pi radians. If you wanted to do this peak to peak, you could measure from 5 pi over 2 if you wanted to. You can measure from 3 pi minus 2 pi if you wanted to. All of these will kind of give you the same thing, and I'll kind of jot some notes. If I do 3 pi minus 2 pi, that's just going to be pi radians. Or we can do 5 pi over 2 minus 3 pi over 2. And again, this should give us 2 pi over 2, which is just pi radians as well. So a bunch of different ways to calculate this. They should all give you the same thing. We're just trying to find one full rotation of our wave. So if we're putting this all together with amplitude, period, midline, we can find it from equations, and then we can also find it from graphs. So looking at this problem here, I always like to start with equation of the midline. I find it easiest. It looks like we have that vertical shift d of 2. So that equation of the midline, if I graph it, is going to be y equals 2. Then my amplitude is just that a variable out in front, so amplitude is 4. And lastly, our period we calculate using b, so b equals 3. So that means my period, if I go 2 pi over 3, that will be how frequently my graph repeats. I'm going to throw that in radians, and I'm going to calculate that out so I can get the decimal answer as well to see what that looks like. 2 pi over 3, 2.09 radians is how frequently we are going to repeat. And let's just graph this in Desmos real quick to see if this equation matches and these features match. So again, we're in radians, so I'm going to change this over to make sure my settings are in radians here. Then I'm going to type in, I got f of x equals 4 sine of 3x plus 2, I think it was. Yep, that looks good. Let me check my equation of the midline. Oh, I lost some stuff there. We had that written as y equals 2. If I throw that in, that indeed looks like that line of symmetry. Let me turn that red and throw a dashed line on it just so we can see. If I count my amplitude, it looks like I have from my midline, I go up 1, 2, 3, 4 units. So that works for me as well. And then if I'm testing the period, I can kind of measure from this starting point. I'm going to, from this starting point, trace up back to my midline. I have not dipped below it yet, so I'm going to dip below that midline again back to center. So this point right here should tell me what my period is. Let me clear out my notes. Right here, and it looks like we reached that after 2 pi over 3. If we wanted to, let's say we didn't have that midline there, we can kind of roughly click and see, hey, yeah, that's about 2.09 like we said. And as we had calculated, you'll see that my notes went away, but we had 2 pi over 3 as our radians there for the period. So if we're not given the equation, we're just given the graph, we can find this stuff pretty quickly as well. Finding the equation of the midline first on example 7. Again, I'm looking for that symmetry, and it looks like it's at 1, y equals 1. So I'm going to draw a little sketch there. I'm going to throw my midline in, y equals 1. My amplitude I'm measuring from midline to one of my peaks. So if I measure from that midline to that peak right there, it looks like I went up 1 tick, 2 ticks. So my amplitude is 2. I'm just going to double check that measuring down as well to make sure I place that midline appropriately. 1 tick, 2 tick, awesome. And lastly, that period, I'm going to use the tracing method. If I start at 0 degrees or 0 radians at 1, looks like my graph goes down, comes up, reaches back to the midline. Notice how I'm not at 1 full rotation yet. I need to keep going up. Boom, there's my 1 full rotation spot. I'm going to kind of just trace that down, and it looks like pi is where I'm at. So pi, or 3.14 radians, is my period.